Test, hello. I know everyone's dying to get out of here, so I'll try and make this as quick as I can. I'm going to be talking about the work I did on 140 and 28 gigahertz millimeter wave measurements for integrated sensing and communications. And that's very wordy, so I'll explain what that means in a second. Oh, and in association with all these universities at the bottom, and my supervisor is also John Drogo back there. Thank you in advance for all your assistance. So what are the motivations of this project? What do we plan to do with it? The number one short-term goal is that we can use these frequencies that are going to be employed in both the current generation, like 5G network signals, and next generation network signals like 6G. That's what the 140 gigahertz application is for. And we're investigating how they propagate in different environments because we plan to roll them out for network communication purposes. Eventually, we need to know how they interact with different surfaces, rooms with people in them, rooms without people in them, that sort of thing. And so in order to study that, we run lots of experiments using both frequencies in a variety of environments. And then a more long-term goal, this is much more far off, but we would be able to use these technologies in smart cities. And I'll talk a little bit more about what a smart city actually is. And they also have indoor applications in workplace safety. So this is the 28 gigahertz platform. It is a lot of complicated machinery, but all you need to know is that it is scanning the environment, spinning around in a circle, and giving us a data set to work with so that we can see how the 28 gigahertz signal propagates through the environment and what kind of backscatter we're getting to see how the signal reflects off of different surfaces. And then this is the 140 gigahertz measurement platform. The main difference between the two of them, even though they are measuring the same thing, is the spatial resolution. So with the 140 gigahertz platform, we get many more data points and a more clear data set, which I will also show examples of in a moment. And this is just the charging station that we use. And that's the TX and RX is an abbreviation of transmitter and receiver. So they're a paired system. I'd like to talk a little bit about the methodology of the experiments. It's a little complicated to explain without any of the actual present materials here, but we have the transmitter and receiver on a cart. And with the 28 gigahertz receiver, what we do is we take it on the cart and we run a short 60-second experiment. It paints the room with its signal, and then we have to move it about a meter all through the room until the whole thing is scanned. So it's actually quite a time-consuming process. And then the 140 gigahertz system is much more hands-off. You just sit the cart in the middle of the room, and you set up, if we're using the LiDAR, you set up the LiDAR in the corner, and then you just let it run for 15 minutes. And that is how you collect data with the 140 gigahertz system. So these are the campaigns I was present for. I was there for I only joined in the middle of July, so I've been present for fewer of the outdoor campaigns, but we've done a variety. We've done labs, lounges, we've done street corners, we've done offices, we've done classrooms. So we're trying to aim for variety so we can see how the signal propagates, like I said. And this is an example of one of the outputs. This is a heat map. This was actually, heat maps were featured in one of the other presentations previously. What this is measuring is the power return from different surfaces in the room. So if you'd imagine the receiver is spinning in a circle, reflecting its signal off of different surfaces, and the surfaces that reflect more power show up as more intense. Those are the red areas. And one of the other people working on the project wrote a program that gets rid of a lot of the background noise. So these are the same heat map, except the bottom one is missing the excess noise from static objects that we don't care about in the data set. And then this is the 140 gigahertz output. It's probably a little hard to tell from the distance you all are sitting, but it's the data points are much smaller. And this little circled box here is actually the motion of a person, which is the way we're using sounder data to tell where different objects are. And we will also talk about the LiDAR outputs. This is probably the most intuitive way of viewing the data. What the LiDAR is doing is painting out the room with beams of light. And then when that returns to the LiDAR sensor, it paints an image. I don't know how well you can tell, but this is us huddled around the LiDAR cart. And we're in a little cafe, I guess, called Joe's Coffee. You can tell this area is an escalator. These are people. That's the register. And using this map, we can very easily tell where the different objects are. And the smart city application I was talking about earlier is that if we can estimate the distances between people and vehicles up here, like we can monitor the motion of this truck, then we can connect the LiDAR to traffic lights, and we can keep the light green longer so that if there's nobody coming, you can just go. And that also improves the safety for both pedestrians and drivers, because the LiDAR can dynamically change stoplights, for instance. If somebody is coming and is at risk of being hurt, they can tell the car to stop. So that's the smart city piece of it. And uh, in the sounder graph, if you don't want to just look at the LiDAR data, here is the motion of the truck. While it is moving, it is a straight line up. And then when it stops, you can also tell exactly where the region that it has stopped is. And then it continues moving again. And that is all visually discernible in the graphs. So that's the main gist of investigating the signal propagation. And that's all I really have to say about the work that I've done on this project. Thank you very much for listening. And now I'll take questions. Yeah, in the front. So the two sampling frequencies are 140 gigahertz and 28 gigahertz, I believe. Millions. In terms of the 140 gigahertz transmitter and receiver, we get millions of data points that are all sorted into a CSV file. And in terms of the LiDAR, there are already services that exist that parse the data for us so that we can view them. And that file is called the .pcap file. So that's how we analyze the data. Well, if we go back to Joe's coffee, if I had to guess, this is where the card is. This is probably about 10 to 20 meters away. So really, it just paints as far as the light beam can go and receive. But it is on the order of magnitude of dozens of meters at least.